Welcome back, physicists. Today we get to start the last section of chapter 5, which is kind of neat. But in here, we are going to be talking, starting today, and I'm sure going through tomorrow, maybe just that, but we'll see. 5.3, we are going to be looking at forces some more, which remember, we looked at a ton of forces, whether it's gravity or the normal force or friction, all these different things. But we're going to make the jump. We're going to look at forces in 2 dimensions. Okay, right off the bat, before we even jump into the main section, I want to do a couple recall pieces. If I'm given a vector, so we'll just say given vector v, or I'm going to say vector f, and that's redundant. If you put the arrow above this, you don't have to write the word vector, just so you guys are aware. With magnitude, and I'm going to really generalize this thing, I'm going to say magnitude r. Magnitude r and angle theta, or at angle theta. Okay. I'm not going to write it down, but I do want to specify, when we measure angles, we always start from the positive x-axis unless you're specified with some bearing. In any case, if you're using this angle theta and you want to use this shortcut that we have discussed and we're just going to make sure we still have, you have to go from the positive x-axis and then rotate counterclockwise. Has to happen. So if we get this, our component vector, or rather we can write f as a component vector. So specifically, we can say, hey, check this out. F is Instagram brackets. And there's a couple ways that I want to be able to think about this. First off, when we think about angles and triangles and stuff, x and y are represented by which trig functions on the unit circle? So sine and cosine are the answers, but the order matters. Which one's x? Cosine. So check it out. If we have the magnitude and the angle measured from the x-axis, we did this work where we went into component form, r cos theta and r sine theta. Now, I don't think we did this in the process of working these out, but is there something that we could probably factor out from both of those that, if distributed, would give us the same thing? R. Now, remember, the theta might be another natural choice, but we can't take it out because it's stuck inside the argument of our cosine and sine functions. But if we wanted to, if it makes it a little bit easier, you could do it like this, especially if it's a really ugly number. So instead of writing the decimal 10 times, if you're doing a bunch of work with these, you can just keep it out front and write it a single time, or 5 times in that case. Cool. There's our recall. Beyond this, nope, we'll get to it. Let's start our first section. So here we go. First little question, what is equilibrium? Talk it out with your neighbor. I'm going to call on somebody in about 30 seconds. The question is, I'm going to rephrase it. When is something at equilibrium? That's a question I want you to address. 30 seconds and I'll find my calculator and call on somebody random. Equilibrium occurs when net forces are equal to 0. So our section today, and I know we already defined it, so I'm not going to sneak in this definition again, but we are going to go back to this idea of equilibrium, and because I'm certain that we already have a section somewhere in our notes called equilibrium, I'm just going to say it's equilibrium continued, and I'm just going to use CONT for continued. Cool. Now, Rafa, you hooked it up right away. We know that equilibrium occurs when the net force acting on an object equals 0 newtons. Really, really careful. This is always an easy place where people get goofed up. Does this mean I'm not moving? No. I could be at rest or I could be moving. What does this imply is guaranteed to be 0 other than the force? Acceleration. This just means I'm not changing my velocity. Whether it's constant at stop or moving, doesn't matter. Okay. All we're going to do today is we're going to extend this idea into 2 dimensions instead. So we're building our way up to our 3-dimensional universe, and we'll start with 2. So here we go, our first little subsection. We are going to define for ourselves what we will call the equilibrant. The equilibrant. Ugly word. When I type this into Microsoft Word, it doesn't think it's a word, so that's something. But the equilibrant. As we're looking at this, I'm going to sketch a little picture over here first, and we're going to be able to logic out and see there's intuition to this. Imagine that we have some object, don't care what it is, and I have it connected with a few massless ropes, or people can be grabbing it, doesn't matter. But hypothetically, somebody pulls at this direction, we'll call that force 1, and somebody pulls over here, and we'll call this force 2. Okay, these people or objects, whatever it is, they're pulling on this thing, right? If it's not stuck to the ground somehow, will the object move, you think? Assuming that they're overcoming friction, let's say it's frictionless surface, I'm even fine with that. Will that object that they're pulling on move, you think? Which direction do you think it would move? So up for sure, some up, and what other direction? So I think, to me, it looks like it would move left, but it just depends on perspective because I didn't give us actual numbers or actual angles. I think the force to the left is probably a little bit more than the force to the right, but I could be wrong. Like, we don't have the actual angles. This thing will move, though, right? Could we add these vectors up? Now, I wouldn't necessarily write this, but if we had the values, if I were to copy and paste force 2, just tip to tail, it'd probably go to about right there, yeah? Somewhere in that range? Which means this line right here that I'm drawing is the what? And I'll just put a little point there, and that'll be the easiest way. This red vector then that we drew, I'm going to make it a little bit more to the left because it does look to the left to me. This red vector is the what? The resultant. So this is FR, the resultant force. Everybody on board with this still? Okay. If I wanted this thing to be in equilibrium, what would I have to do? I would have to apply another force somewhere in some direction. Where would I draw the other force to make it so this thing doesn't move? Riley hit it right off the bat. Down and kind of to the right, I think. So check it out. I'm going to do it in purple. Would this do it right here? Not quite. How come? It's not the same what? You said it's not equal. We're so close. Good. They're not the same magnitude. The direction's good because it's opposite, but it would have to be the same magnitude, right? So this roughly, if I'm, hey, that's actually pretty stinking close, I think. This is the ugliest subscript that we're going to use. I'm going to use equi for equilibrant. Equilibrant. I can never decide where to put the emphasis. Okay. Going through this, logically, intuitively, can we all agree that one person could pull right there and it would counteract? Okay, we're going to call this the equilibrant, which means we just have to define it. We're going to say that by definition, easy to do as well, and I have space, it'll take a line or two, but the force required, or needed, because it's a shorter word, to put a system in equilibrium. That's it. It's the force required. Now, on this picture, I've drawn a single equilibrant in here. Is it possible that there were two other people that produce force 3 and 4 that create this equilibrant force in the end? It could be two different people pulling, just like we had two people pulling from above to make that resultant force. We could have more people pulling so that the resultant force in the opposite direction just counteracts it. When we look at this, there's an easy way to see this. If we want to calculate out or to find our equilibrant force. Turns out that it is just equal but opposite to which one? How do we decide we're going to draw that purple line? It was equal but opposite to what? The resultant. Check it out. It's just negative the force of the resultant. Easy. Now, if we break this into components with x and y using those cosines and sines, respectively, this problem becomes fairly easy. So, here we go. We're going to do one problem. This is the only one that isn't on your worksheet examples that we're going to look at, so I'm sorry about that. Using a little bit of editing magic, Nick, you're going to have to pause it. Hopefully you're watching this. My favorite color is green, Nick. When I ask you tomorrow when you get back, you better be able to tell me my favorite color is green, Nick. So we have Tim and Bree pulling on this from the same point, and we'll sketch the free body diagram here in just a moment. All we need to know is the third person, Al, we'll call them, how hard and which direction they have to pull so that we're at equilibrium. Before we tackle this whole problem, I'm going to give you a moment. I want you to draw your free body diagrams. Remember, if we have bearings, you need to have some way to indicate north and south, right? I would use, and I will use rather, I hate this color, but you guys can kind of see it. That's okay, I don't want to see it hardcore. Let's say I'm just putting this here to be east, north, south, and west, so I have like places to pull from. If I were doing it on paper, I'd use a dotted line. Here's the object they're pulling on. I want you to draw me the free body diagram first. Cool. I'll give you a minute. I'm going to come around and critique your drawings just to check. If you're having issues, be sure to check with me while I'm walking around. If you're struggling, I'm just going to pick different colors. Okay, I want the first color that comes to your mind. Okay, Riley? Tim.
Blue.
Okay, Tim is blue. Bree should be blue because of the bees, but that's all right. Cool. I'm going to draw Tim's force here. Where do I start if I want to draw this vector? So I start at north. There it is. And I'm going to make it darker blue. Start at north, cool, and then I fall which direction? Is east to the right or to the left?
Right.
To the right, and probably about there. Okay, I'm going to, let's see, Tim's is 75, so I'm actually going to make that a little bit shorter so that I don't have to make Bree's like ridiculously large. As we're here, I'm going to make sure that I label this F sub. What do you think we should use as a subscript for Tim? T is a good choice. Do not confuse this with tension. Okay, other part, and this is where we just have to make a decision. I would not jot this down yet, but I know that this is my 30-degree angle. Everybody on board with that? Is that really the angle that we should use, though? Rafa, you shook your head no immediately, and I hope everybody can answer this because I alluded to it a few minutes ago. When we're dealing with these angles, we always measure from where? The x-axis. I'm okay with this being 30 degrees. That is in fact true. But the angle theta that I'm much more concerned about is going to be this angle right here. And what is this angle right here? If that's 30, this must be 60 degrees. Okay. And then the only other thing that I'll add, I'm just going to put this on here. I'm going to avoid the double vertical bars for the magnitude just because I think that it's unnecessarily ugly for our purposes. Tim pulls at 75 newtons. Cool. All right. First color comes to mind. Delilah. Bree. Purple. Okay. And let's see. Where should I start if I'm trying to draw Bree's vector? So I start at south, which is down, and I go 45 degrees which direction? I go to the east, and it's a little bit stronger than Tim, so I'll make it a little bit longer. And 45 degrees, I think, is not even think. I know it's right there because I have nice graph paper. Cool. There it is. That's the force of Bree pulling at 90 newtons. And I'm going to do something similar here. This angle we know is 45 degrees, but that's not really the angle that I care about because I'm always going to go from the x-axis. You have two options. There's going to be one that's more natural. I could make the claim that she's pulling at 315 degrees. Do you agree with that? How on earth did I get 315? I just went the long way around. Is there a better way rather than saying theta is 315 degrees? Instead of starting here and going all the way around, which is what we normally do, could I go this direction instead? And that changes the sign on it to what? Negative. That's super important. And that'd be negative 45 degrees. Everybody cool with that? I'm using these angles purely because my bow ties and butterflies. When I make this a triangle, I want this to be my right triangle. When I make this a triangle, I want this to be my right triangle. We do not have to draw it out. Question? I mean, yes, but what was your question?
It doesn't matter which side is 45.
It doesn't. But if you're going to look at this one, you would probably wind up using positive 215 or 315 because you would take 270 plus that other 45. Okay. What direction is this object going to move if nobody else acts on it? It's going to move to the right. That's one direction. Is it going to move up or down, do you think? You think so? Maybe. I can't tell for sure. The only reason I say I don't know is because maybe 75 times the sine of 60 winds up being stronger than negative 45 or sine of negative... Oh my gosh. We'll check. Let's figure it out for sure. Okay. So as we're looking at this, we want to make sure with some sense of consistency. Let's see. Nobody's green yet. I'm going to make Al green here in a second. But I'll use red for the meantime. What do we know about this problem? And let's just try to make sure that we can write this out. What's the force of Tim, the magnitude there? I already have it written, and I know it seems redundant, but it's good practice. Tim pulls with 75 newtons of force. Is that a lot?
It's like, what is it at like 75 pounds?
Way too big. It's about, like, if we think about this, gravity is 9.8, right? I can't divide by 9.8. But I can roughly divide by a number that's close to that. What's close to 9.8? 10. If I divide this by 10, I get 7.5, right? Which is roughly the kilograms of this. This is like 15 pounds of force. Everybody can do this. He ain't pulling very hard. Cool. All right. If I want to be able to talk about the angles specifically without getting goofed up, we know Tim's angle is 60 degrees, right? Do you guys have a suggestion for an easy, convenient way to write Tim's angle? It's going to be theta, I guarantee it. But if I just write theta, there's an issue because I get several thetas in here. How do we indicate it's Tim's force? Sub t. How should we indicate it's Tim's angle? Sub t. Let's do it. Cool. And that's 60 degrees. Notice I've made the change. We're using it from the x-axis. This is going to happen consistently. All right. Give me the same stuff for Bree. I'm going to let you write it first since you already have it. If you want to work ahead, you can, if you're confident with where you're going. Bree's force, I think, is 90 newtons. And theta sub Bree is negative 45 degrees. The negative is going to be super duper important. Do not lose it along the way. Cool. Well, what are we trying to find? Cool. All right. What are we trying to find? Number 3. Force of Al. I'm cool with that. F sub A is what we're after. If you want to be more specific, it's the what force? Equilibrant force. Okay. Al is the equilibrant force. I'm looking for force of Al, and I'm looking for the theta of Al. Now, I'm going to put some commas or equals just here, but there's one more thing that I need, and I'm going to move this example so I have a little bit more space here in a moment. Actually, let's see, I don't need any of that. So we'll do that. Let's copy. Just kidding, we'll cut. We'll do that, and we'll go, pa-da. Look at that. Now it all fits. There's one more thing that I need, though. To get an equilibrant, it's just equal but opposite to the what? The resultant. So if we can find the resultant of these guys, we'll be golden, and we'll get it. So here we go. I'm just going to say the force of the resultant. And if we want to be specific in a problem, like if we're going to leave this and come back to it later, I would probably say the resultant of T plus B. And this is a Holloway notation, just so you know. This is something that I do just to keep stuff straight if I need to. Cool. Well, let's get to it then. Here we go. We're going to look at equation or the work that we're going into this. And let's knock it out. I need to find the resultant force. To do this, it would be so much nicer if I could write a singular vector that represents Tim and Bree. I need to be able to add them, but I can't really add them right now in a nice way, can I? Can we write Tim and Bree's forces in component form? Meaning Instagram brackets. Do we have an angle and a magnitude? Oh my theta, we can. Cool. I'm going to do Tim's. I want you guys to do Bree's. If you need to wait a second because you're not quite sure, all I'm going to do is use exactly this. 100%, this is what I'm using, where r was the magnitude of the vector. So I'll do Tim's, and I will grab my calculator. Double, triple, quadruple check. Your calculator needs to be in which mode? Degrees. Cool. Force of Tim, and I like to use this shortcut that we discussed. 75 times the cosine of 60 degrees and the sine of 60 degrees. So let's see, cosine of 60, that's going to be 37.5. That one's an ugly decimal. Yeah, that seems believable. Bless you. It's not funny. I don't know if you guys heard Miss Val chuckling. Somebody, if you're ahead of me, please double check. That's what I get for Tim. So 75. Why 90? Terrible. I think that you're getting goofed up. Without looking at mine, don't look at mine, okay? How hard? What's the magnitude of 90 newtons? Replace that. What's her angle theta? Good. That should be negative 45. Okay, I have no idea what this is. Whatever root 2 over 2 times 90 is, 45 root 2 will get you the same number. I don't know. Somebody want to shout it out? Force of Brie. I assume you guys did 90 cos negative 45, sine negative 45? Okay. Somebody that already has a number, do me another favor. Take 90 or 37.5 times root 2. It's going to sound weird. 37.5 root 2. Let me know what that number is. Is that the same thing that you got when you did your other calculation? 53 something? Interesting. It should be the same number. It is the same number? Okay. Weird. I'll double check that here in a second. You got 63 what? 4 of them. 6396? Hey, and I know that this is going to be the exact same. Just negative. Right? It should be. I wrote 69 there because I had the 6396 in my head still. Thank you. 63. Thank you for that. Cool. Oh, that's ugly. Awesome. Looking at this, up or down in the end? Can you tell me just from these numbers? It's going to wind up going up. How did you come to that conclusion, Fern? I agree with you. When we add the y's, we wind up with a positive y value. Tim wins the up contest here. Cool. So I'm just going to write this, the force of the resultant. And can I bail out of this notation right now? Can I just call it the resultant? If you want to call it Tim plus Bree, you can. Let's get it. This resultant force winds up being this guy. So all of a sudden, let's add these up. When we add up the x's, 37.5 plus 63.6396, what do you get? And again, just in case, we're taking this x value plus this x value to get the resultant x value. All my stuff just has sines and cosines because I didn't have a calculator as I was doing it. What? 101.1396. Okay, I also need the y component. $1.2 something. 26 what one?
1.2604.
04. Can somebody second those values? I suppose I can as well. Cool. All right. Right now, all that we know is that my resultant force, and I'm going to sketch it here. You do not need to. You are going to have a little tiny bit of homework. It's going to be to finish this problem, but I'm going to like push you through it here. My resultant force winds up somewhere over here, just barely an angle. This is where it ends up. Okay, I need to balance this. But before I can do that, I guess maybe not. Maybe we can even make this easier, but I'm going to let you make that decision. If I want to actually find it, I know the components of the end force, I think. What I want you guys to do for me this evening, and this is just a triangle, right? This starts at the origin and it goes to this x value and this y value, which means it's a right triangle. For the follow-up, what I want you guys to do this evening is I want you to find two things. The magnitude of this resultant, which you may need to look back at your notes if you don't remember how to do it. Remember that this is just this symbol if you're looking at your notes. This is double bar. And I want you to find me angle theta of the resultant. If you need to sketch a right triangle and put these numbers on it, it will probably help. You are going to be using inverse SOHCAHTOA in some fashion. Other than that, you guys have a wonderful day. I hopefully won't see you tomorrow, nor you. Remind me in pre-calc to get you a practice test, and I'll try my best to get a practice test written for physics stuff, because we're getting near it, and I'll send you guys with those copies so you can work together. Cool. All right, Nick, don't forget, my favorite color is green.